going down. So it's my pleasure to introduce Helen Janiszewski, who's visiting us today from just across the city over at Carnegie DTM. All right, she's been there about 4 months? Yeah, starting out as a postdoc working with Laura Wagner. So let's give her a really warm welcome, and she'll talk today about new insights on the structure of Cascadia subduction, the Cascadia subduction zone. So let's give her a warm welcome.
Okay, is this good? Good, okay. Up, how do I, good?
Louder.
Louder, okay. Okay, so yeah, thank you all for coming out here today. It's been a real pleasure to meet with some of you and see the department. So as Nick said, the title of my talk is New Insights on Structure of Cascadia Subduction Zone from Amphibious Seismic Data. This is work from my PhD, which I did at Columbia with Jim Garrity and Jeff Abers. Zach Alon also contributed to looking at some of the noise in these data. Haiying Gao contributed the amphibious ambient noise results, and Alain Cartanen and Bissell contributed to the active source portion of this study. And so the overriding question that's going to drive this talk is, what can amphibious seismic data tell us about the Cascadia subduction zone? And I'm going to give you 3 motivating points that I'm going to return to in this talk today. Just briefly, first question, what can we learn about the evolution of a plate from its creation at a ridge to subduction and beyond? How is structural heterogeneity linked to variations in subduction behavior? And what does the transition from locking to stable sliding along a subduction plate interface look like? And I'm going to go through these questions in more detail. So for the first one, we know this is our study area, and we know that we have the Juan de Fuca plate here. The Juan de Fuca ridge is about 500 or so kilometers offshore North America. This is Washington State, Oregon State, California. And we know something about what we would expect an oceanic plate to look like. We know that it's high temperature and melt beneath the ridge where the plate is being created, moves away from the ridge, it cools, and then at some point it hits the continent and it subducts and goes underneath the North American plate. But what about the details of that structure? And to understand that, the tools that I'm going to be using are seismic data from this large-scale community project called the Cascadia Initiative. And this was a community experiment that over 4 years deployed these OBS seismometers, ocean bottom seismometers, all over the entire Juan de Fuca plate, extending from the ridge to the margin, and then also this backbone of onshore seismometers. And this gives us the ability to, for the first time, seismically image an entire plate from its creation at the ridge to where it begins subduction, and then look at the subduction processes onshore on much finer detail than we can with global studies. So we can really start to look at this on a much finer scale. And I should mention, almost all of the results I'm going to be presenting today are from this Cascadia Initiative experiment. As I said, it was a community experiment, so I have to acknowledge everyone that was part of that team in planning it, the people that went out doing field work for 4 years on the ships, going and deploying these instruments, getting them back. And it wouldn't have been possible without the American Relief and Recovery Act, which really funded the deployment and engineering of some of these new instruments. So thanks, Obama. The second question, how is structural heterogeneity linked to variations in subduction behavior? So we know that there are hazards associated with the Cascadia margin, namely megathrust earthquakes. We know that it's possible to have approximately a magnitude 9 earthquake rupture along the coastline here. This is showing you just a comparison of the 2004 Sumatra earthquake slip area, and it's thought to be comparable to that, overlaid on top of the west coast of the United States. And of course, there's a line of volcanoes onshore, so that poses societal risk. We also know from other geophysical and geochemical studies in the region that there's heterogeneity associated with these features. So for example, this is modeled slip. So the red colors mean higher amounts of slip, blue colors mean less slip. This is based on paleoseismic studies of previous megathrust ruptures in the area. And they see that it seems to be that there are these large patches of larger amounts of slip going down the coastline. It's not just a continuous line of slip associated with these megathrust earthquakes. Similarly, in the Cascade volcanoes, quaternary Cascadia volcanics show that there is more voluminous magmatism, magma production associated with the southern Cascades relative to the northern Cascades. So how does that then relate to some of the seismic features we're going to see in the crust and the mantle? And then finally, the third question, what does the transition from locking to stable sliding along a subduction plate interface look like? We have an idea that there should be variations in seismic locking related to features such as variations in pore fluid pressure. This is from Safer and Tobin. So it proposes that overpressure exists where we have episodic tremor and slip, and that there should be relatively less pore fluid pressure within the locked seismogenic zone. And those features should be observable in terms of seismic reflectivity and in terms of seismic velocities. However, while onshore in Cascadia, there have been numerous studies that have seismically imaged the structure associated with the plate interface, this being one of them from Abers et al. 2009, where they see this low velocity zone within the upper several kilometers of the downgoing Juan de Fuca crust. We really don't know what happens to this structure as we continue offshore. And that's because up until recently, we didn't have offshore seismic stations to make these kinds of measurements. So it's a question whether or not this low velocity zone continues to where the majority of locking is in Cascadia. So this is something that we're going to be able to now address with these new ocean bottom seismometers. So how am I going to be addressing these questions with my research? And in case you haven't seen the title of this talk, the hint is that it's going to be using seismic imaging. Everything I'm going to be talking about today is seismic results, and I'll be putting it into this broader context to try and start answering some of these questions. But just to give you a brief overview of the approaches that I'm going to be using, so we're all more or less on the same page, I'm using 3 different types of seismic imaging in my research, and they have varying sensitivities and strengths and weaknesses, and I'll go over them briefly here so you have an understanding of that. So the first is Rayleigh wave phase velocities that have been recorded as part of the Cascadia Initiative. These are waves where an earthquake has happened somewhere on the other side of the globe. It's recorded along at this seismometer, and these are surface waves, or waves that travel along the boundary layer with the surface of the Earth. They have a property that's called dispersion, which means that different period waves travel at different seismic wave velocities. And this is because shorter periods have a shorter wavelength, they sample less deep into the Earth. And so in general, seismic velocities increase as you go down into the Earth. So these are most sensitive to the surface or shallower structures. And then as you get to longer periods, you start getting sensitivity to deeper and deeper structures. So the main thing to remember about this type of data when I'm showing you the results is longer periods are generally reflective of deeper structures, shorter periods are generally reflective of shallower structures. And this is going to allow us to investigate the entire study area, including the plate evolution prior to subduction, as well as some of the larger scale heterogeneity associated with the subduction zone. Another area of research has been developing new tools for using this OBS data. So there's aspects of this study, including the use of shallow water instruments that really wasn't done before. And part of this really had to be explored to both use the shallow water instruments and also be able to use in an efficient manner over 200 OBSs and correct for noise problems in them. The second technique that I use is something called receiver functions. Again, this is where you have an earthquake that occurs somewhere globally, and the waves are recorded at a seismometer in Cascadia. And the key difference between this and the surface waves is that these are sensitive to abrupt changes in velocity. So these are sensitive to boundaries, whereas the surface waves gives us a more average picture of the seismic velocity properties. Because this is sensitive to boundaries, this technique is really useful to allow us to investigate more detailed structure along the plate interface. So that's what I'm going to be using to present to you today. And so the particular area where we're focusing is right here in central Washington. We're going to be extending the seismic results that I showed you in that introductory slide from Jeff Habers offshore. So we're now going to have new constraints on what the plate interface looks like in what is broadly thought of to be the lock zone. And it's also useful because we can leverage complementary constraints from the surface wave seismic shear velocities in a Bayesian joint inversion, since the previous result gives us this average constraint, and this gives us a constraint on abrupt boundaries. We can put them together in a joint inversion. And just another side aspect of this research was also just generally evaluating the viability of using receiver functions for offshore seismic imaging. It's been very, very challenging in the past. So we have demonstrating where we have successes and where we don't was another point of interest. And then finally, the last technique that I'm using is active source reflectivity from wide-angle seismic data. This again is going to be focused on the plate interface structure. However, it is higher frequency, and it's a bit of a different ray geometry. Instead, this is where we have the Langseth offshore, pulling air guns behind it, shooting, and these signals are recorded by the seismometers on shore after they've somehow interacted with the downgoing crustal structure. And so it's complementary to the receiver functions. We have these results in the same area, so we get to look at this lower frequency and higher frequency results and compare them. And so we just have an added method of looking at the plate interface structure. So onto the broader plate scale structure. So this is an example of the Rayleigh wave phase velocities that we get that are recorded across this entire array. For those of you who look at surface waves, this is just an example of the recording of a single event located here in the South Pacific, recorded at the array. Gray are the instruments, are the seismograms that have been recorded by the OBS data. Black is recorded by the onshore data. And so this really demonstrates that we have pretty comparable quality of signal both in our OBS data and our onshore data after we've gone through the process of correcting for noise in our OBS data. And the Rayleigh wave phase velocities are going to give us longer period constraints extending from about 20 to 160 seconds. The other side of surface waves that we use is something called ambient noise. This is where we're just recording the ambient noise field of the Earth on all these seismometers, and we can then use cross-correlation to measure the velocity at which that signal is traveling between these seismometers. This is an example, again, of the ambient noise data. The red colors are stations that are onshore. Sorry, I should mention that these are all paired with an OBS station. So the red are pairs between an OBS and an onshore station. The dark blues are OBS to OBS. The grays, which you can barely see, are shallow water OBSs. Because of the period structure, this technique is very difficult to use on shallow water OBSs, and the fact that you can't really see the light grays is a good thing because the data don't look that good anyway. But we get really good cross correlations between deep OBSs and the onshore OBSs. And if you're a seismology nerd like me, you'll notice that all the way even out here, just at this raw data level, you can see that the oceanic cross correlations are moving faster than the onshore cross correlations, which is what you would expect given that the oceanic ray paths should be sensitive to oceanic mantle, whereas the continental crust should be sensitive, on the continent it should be sensitive to continental crust, which is much slower at these periods. And this is going to be giving us shorter period information, so shallower information. So here are the results that we get. And so these are our phase velocity maps, again, going from 10, 15, 20, 40, 60, 100. Longer periods are imaging deeper structure. Each of these, the colors represent phase velocity. Blue colors are faster phase velocities. Red colors are slower phase velocities. Typically in seismology, faster phase velocities will be associated with cooler temperatures. Slower phase velocities are associated with things like melt or hydrous phases generally. There can also be variations in composition that can change, affect these phase velocities. But in general, you can see that we have really good coverage over our entire study region. And already at this scale, there should be some major features jumping out at you that you should be able to see, and we're going to talk about them in more detail. Before I go into that, though, I'm just going to show you a brief comparison with previous results. So this, in terms of phase velocity maps, is the first amphibious result in this region, meaning that it's both offshore and onshore. Haiying has published shear velocity models that are amphibious using surface waves. However, she uses a slightly different technique that doesn't produce phase velocity maps, so I unfortunately can't compare it to hers. But this is just 4 recent studies, 3 of which have been onshore, 1 of which was entirely offshore. And in general, you can see that there's pretty good agreement. We're seeing a lot of the same features that have been previously seen, with a few exceptions, probably most notably in the Forearc. So we now really have nicely resolved these 2 linear areas of slow velocities separated by a region of faster velocities, which you can kind of sort of see hints of in these previous studies, but they've been pretty hampered by the fact that they don't have stations offshore to really see that structure, that slow structure at the coastline that does extend offshore. And then similarly, the offshore result, while it does see slower velocities in the Forearc relative to the oceanic plate, it doesn't image the very, very slow velocities that we're seeing along the coastline. So this really is demonstrating how this amphibious approach is getting much finer resolution, particularly in the Forearc, and even abutting the start of the arc here. So, going back to our first question, what can we learn about the evolution of a plate from its creation at a ridge to subduction and beyond? And if we look at the plate, I mean, one of the first things that should jump out at you is it looks really blue, which means it looks really fast, particularly at shorter periods. And as I alluded to before, this means that in the oceanic part, at these periods, we're mostly already sampling oceanic mantle since the crust is much thinner. Onshore, we're still sampling continental crust, so that leads to the very strong dichotomy between the fast oceanic velocities at short periods. And you can see that as we get to longer periods, once we start to be sampling mantle in both regions, that kind of demarcation line at the coastline goes away. Another thing to notice is along the Juan de Fuca and Gorda ridges, we can see that velocities tend to be a bit slower and then they get faster as we're moving away from the ridges. And this is still continuing at 60, and even at 100 kilometers, we're still seeing that signature. However, we can ask a more quantitative question because we have models for what we think thermal conductive plate cooling should look like in terms of these seismic velocities. And so if we generate a model from simple half-space cooling models with seismic parameterization to get the seismic velocities for a given mantle potential temperature of 1350 at the ridge and an average grain size or constant grain size of 1 millimeter, we find in general that we really have a hard time fitting the range of velocities that we're observing with a simple thermal conductive cooling model. So this is the difference between our observed phase velocity and our predicted phase velocity. Red means that our observed velocities are slower than the predictions, and blue means they are faster. So there's a few major features. Again, this is 20, 40, 60, 80, so shallower features, deeper features. The first major thing you'll notice is that at the ridge, pretty much at all these periods, our observed phase velocities are slower than what's predicted. And that most likely has to do with the fact that these thermal plate cooling models don't take melt into account. And so this is indicating that there's a substantial amount of melt upwelling beneath the ridge, starting quite deep and continuing up to shallower depths. However, another interesting feature is that the center of the plate, particularly in this southern region, is faster than what we would predict. And even if we account for the fact that we have the melt at the ridge and try to adjust maybe the temperatures a little bit and see if we can fit this a bit better, it's still quite difficult to explain how fast this gets through thermal conductive cooling alone. And that's a bit of a mystery. One of the proposed mechanisms in other seismic papers in this region using different techniques that have seen more or less the same result suggests that there's dynamic upwelling of melt beneath the ridge and that beneath the center of the plate that is coupled by this dynamic downwelling that is anomalously cooling the plate. Maybe there's also just something more subtle going on with subduction here where thermal plate cooling doesn't quite apply to such a small plate that is so close to a subduction zone where it's already being bent, almost halfway out towards the ridge. Another feature that we see are these patches of red right along the deformation front, particularly right here along 45, 45 degrees north, which starts at about 20 seconds, continues down to about 60. And these can't really be explained by uncertainties and perhaps the sediment that's covering the plate, unless it's significantly more than the values that we've tested. And it's about in the same location that a recent active source study suggested that there may be elevated pore fluid pressures within the lower crust and upper mantle. So maybe we're also seeing that same signature in these surface waves. However, an important thing to note with that is that in general, the velocities along the deformation front are not anomalously slow, which would imply that there is not widespread pore fluid pressure and hydration along the entire deformation front, and seems to only be in these couple areas and maybe up here in the north and south close to the Blanco transform as well. Moving on to the second question, how is structural heterogeneity? And we're going to link to variations in volcanic behavior first. So if we look at the Cascades volcanic arc, again in these map views, we see this line of relatively slow phase velocities beneath it. And if we look in more detail, there's a very obvious along strike trend, which has been seen before, but this is giving us a nicer picture of how centered these slow velocities are directly beneath the arc and in the back arc region. So this here is showing you difference from mean phase velocity along an averaged region. This is latitude here on the y-axis. So the northern volcanoes are up here, Mount Baker Glacier Peak, continuing down to the southern volcanoes, Medicine Lake, Mount Shasta. Each one of these lines is a different period. Points that are on this side of the line are slower than the average velocities along the entire arc. This side of the line are faster than the average velocities along the entire arc. And we see both in the arc and the back arc, in general, the southern velocities are much slower and the northern velocities are faster. And if we compare that, this lines up pretty well with the variation in quaternary volcanics, where the northern volcanoes that have produced less magma correlate with higher velocities, which is roughly what we would expect in terms of melt production. But interestingly also, they also correlate quite well with variations in heat flow. And so this higher heat flow that is observed in the southern Cascades it nicely correlates with the onset of these slower velocities. And actually, Christy Till, Adam Kent, Jeff, Jim, and Brad Pitcher and I have recently been comparing this a bit more quantitatively, and we see very, very nice correlation between these velocities and heat flow estimates, which suggest that these trends are dominantly explained by variations in a lower crustal and upper mantle magma input to the system. So then the next question, again, how is about structural heterogeneity, but now asking how it is related to variations in slip in subduction behavior. And for this, we're going to go to the Forearc. And so that is this area extending from the beginning of the deformation front before the arc, encompassing the coastline. And I've plotted this such that these velocities are saturated so that you can really nicely see the variations. This is, again, extending from 10 to 60 seconds, progressing to deeper sensitivities. And you'll notice immediately that there's this line of slow velocities at 10, 20, not quite as slow, but still very slow, and a little bit more patchy, 40, velocity is still in about the same place, and then all of a sudden at 60, that variation in slow velocities along the coastline is gone. So what is that, and how does it relate to what we know about past seismic rupture and slip behavior? So there's estimates of paleoseismic rupture that have suggested this segmented megathrust rupture in the past. There's also something that people have measured, these Bouguer gravity anomalies. And the blue regions that are kind of outlined by these white areas, those are areas of low Bouguer gravity anomalies that have been generally correlated with deeper sedimentary basins. And they also approximately line up with areas of estimated maximum slip in past paleoseismic rupture. If we overlay those Bouguer gravity contours on top of our phase velocities, we see that they really nicely align, particularly at 10 and 20 seconds, with where we're seeing this, these slow velocity features. Both along the dip direction and even along strike, we see that some of these features up in the north by the Olympic Peninsula and in the south by the Mendocino Triple Junction seem to correlate with these Bouguer gravity anomalies. At 40 seconds, again, there's still a decent correlation, although they've moved slightly landward. And so this is important because in general, when we think about these phase velocities, we think that, you know, if we're in an oceanic setting, if we're in a continental setting, sure, we need to invert them to understand what depth the features are at. However, we can say, okay, a 10-second feature in the ocean and a 10-second feature in a continent, they're basically reflecting the same depth of feature. That's not true if you have a lot of really, really slow sediment. And so maybe these slow velocities, particularly at 10 and 20 seconds, aren't suggesting anything about deeper structure, but instead the 20-second sensitivity might be shifted up to reflect just the very, very thick pile of sediments that are associated with the accretionary wedge in this region. Another thing to look at is the tremor density. This occurs, episodic tremor and slip in the region occurs down dip of where past megathrust rupture has occurred and where locking is occurring. And if we overlay the tremor density contours on top of this, we see that they are consistently down dip of where these slowest velocities are. Even at 40 seconds where those slow velocities have moved a little bit landward, the tremor density, highest tremor density is still occurring down dip. So in terms of precisely what these velocities are, whether or not the relative contributions of the sediments, if there maybe is some sort of hydration signature or released pore fluid pressure, pore fluids or dehydration associated with these slow velocities in relation to being up dip of the tremor, that's something that we can't really say specifically just with this data. However, one thing is that the correlation where these slow velocities at 40 seconds seem to be occurring up dip of the highest tremor density regions does suggest a correlation and maybe suggest that some along strike heterogeneity in the downgoing plate does influence the variation in tremor density along strike. Now I'm going to move to focusing on the second part of my research, which is really focused on this plate interface scale structure. And we're zooming into a much smaller focus area. So here again, this is Central Washington, North American plate, Juan de Fuca plate, and there's a focus area of seismometers that were deployed. The colors are just something about essentially signal to noise ratio for using receiver functions. So unless you really care about quality of offshore receiver functions, you can ignore that. But I'm going to be showing you the receiver functions from this subset of stations right here, and we're going to be using that to look at what the plate interface structure looks like. And this is an example of what offshore receiver functions look like, and it will hopefully show you how difficult it is to do them, but also how surprisingly robust these results are for all the difficulties that are associated with offshore receiver functions. Just again to remind you, we have now switched to the regime where we're thinking about abrupt changes in velocity. And in this convention, black are positive arrivals in the receiver functions, gray are negative arrivals. And what I'm showing you here are each individual stations. These are the receiver functions calculated, all of them that we can use at each one of these individual stations. I'm showing you 5 shallow water instruments, 1 deep water instrument for comparison, and then using the same exact time period, an onshore instrument using the same exact signal to noise criteria. And so you can see just based on the density of this plot, how much easier it is to get receiver functions onshore compared to offshore. But one of the key things about this is that we have consistent arrivals at individual receiver functions at a station, and then also across multiple stations, we see consistency in these arrivals. So this positive is coming in at about 3 seconds, followed by a negative, and down here again, there's a strong negative. In this area in the middle, it's a little bit mixed and matched. But in general, we're pretty confident that these are reflecting real structure due to the consistency across individual receiver functions and across stations. And so, as I said in the beginning, we're going to do a Bayesian joint inversion for a shear velocity model using the results from one of the stations at the receiver the receiver functions at one of the stations, which is located here, and as well as the phase velocities from our surface wave results. And one of the benefits of this Bayesian inversion is that it's we put in a very, very simple 3-layer model. It runs 500,000 iterations, and it gives us a probabilistic result. So it really tests the model space quite well. And this is our result. So this panel is the shear wave velocity. This is going down in depth. Vs is here on the x-axis. Red colors indicate higher probability, white indicates low or 0 probability, and the black line going through this is our best fit model for our results. This is just the data and 10 example synthetics compared for the receiver functions, a similar result for the data and synthetics for the phase velocity result showing you the fit. And then this panel here is just showing you the probability at any given depth that it is an abrupt velocity boundary as opposed to some sort of gradient or smooth boundary. So the higher this spike is, the more confident we are that really is an abrupt velocity boundary. So there's a few major features in this. So we start out, relatively slow, goes down, and all of a sudden about 16 or so kilometers depth, we get this really large low velocity zone. And that is at about where we would expect the plate interface to be, based on models of the subduction zone. Then beneath that, this is about 5 to 6 kilometers thick, so about as thick as we would expect the Juan de Fuca oceanic crust to be. And then we get into mantle velocities, so this would be our subducting moho. So it matches well with what we expect the general tectonics to look like, and this is a really strong feature. It's actually, in all of this, it's the highest probability abrupt boundary in the entire model. So we have this low velocity zone that's being imaged offshore in what we think is this broadly locked region. So this comes back to this question of what does the transition from locking to stable sliding along a subduction plate interface look like? And now this is starting to fill in all these question marks in this area, and we see that there does appear to be a thin low velocity layer at the plate interface within the broadly predicted lock zone. And perhaps that is indicating somewhat weaker plate interface extending offshore. But as I said, another way we can get at this problem is using this wide-angle reflection data. And it's complementary to the receiver functions. Right here is the location of the station that I just showed you, where we have the shear velocity model from. And then we're using these stations onshore. This is the line which the Langseth traveled along. And so it allows investigation of the plate interface in a similar area. And this is an example of the active source data that we have. So this is travel time. This is shot to station offset. And each one of these kind of big black ringy things is some sort of an arrival. And unfortunately, because we don't have two-directional data, we really can't do active source tomography to get a good independently constrained velocity model. However, there's been a lot of active source studies in this region, so we have fairly robust forward estimates of what velocities look like. So we use that to basically investigate what are the plausible features, what are the plausible ray paths that can be generating these features in the seismic data. And yeah, and just to remind you, this is kind of the geometry we're looking at. So, you know, the questions are these rays that are just traveling within the overriding crust, or are these rays that are somehow interacting with or reflecting off of structures associated with the downgoing Juan de Fuca crust? And I'm not going to show you the details of all of this for the sake of time, so you'll just have to believe me, and if you have questions, you can come ask me later. But through a series of forward modeling tests, we can figure out that these arrivals labeled A1 in brown, which move at about 5 kilometers per second, those are ray paths that are within the overriding crust. They don't interact with the subducting plate in any sort of way. However, these A2 arrivals are modeled as reflections off the subducting plate interface. And we do a series of tests to see if they can be explained as reflections off of the subducting moho, and they can't, based on what we know about what the velocities should be. They really have to be reflections off of the plate interface. And if you notice, there's these particularly high amplitudes at near offsets that seem to die out. And also you'll notice that this feature is seen on this station, but it's completely absent on this station. So what is the cause of the high amplitude arrivals from the plate interface? And we do just some very, very, very simple estimates of relative amplitude. And again, here I'm just going to show you some data of a couple of different stations. So we've taken the Hilbert transform. It's basically just for visualization purposes for this figure. And high amplitudes are going to be in red. Low amplitudes are going to be in blue. I apologize if anyone's colorblind. I realize that this is a horrible figure, so I will fix it at some point. However, This station, CW01, is closest to the coastline, and so we would expect less attenuation, less loss of energy. And you'll notice that there's really no evidence whatsoever of any sort of high amplitude arrivals coming in here. CW03, there's something coming in here, but it's not as high amplitude as these first arrivals, and this is moving inland. Again, CW04 further inland, and now we really do see these high amplitude arrivals, and they're higher amplitude than the nearer offset arrivals here. And CW06, even further inland, really high amplitude arrivals relative to the nearer offset arrivals. If we do a comparison between some predicted reflection amplitudes just based off of very, very simple ray tracing, we see that these amplitudes line up with this onset of very high amplitude reflections, which is just due to approaching the critical angle of incidence. However, the main thing to take away from this is that here and here at these two stations, they line up. Here and here, given the assumptions of plate geometry that we have, we still predict that there should be high amplitudes, but there are none. So what is causing that? And this is kind of the ray geometry that we're looking at. And so here are the stations. These white ray paths are ray paths for stations where there's no high amplitude arrivals. Gray is this intermediate, and then black are like these stations where there are high amplitude arrivals. And what we find is that if we look in more detail about where we would predict them to be interacting with the plate interface, the no reflectivity region is farther up dip. Then there's this kind of transition zone, and the higher reflectivity region is farther down dip. And if you remember, coming back to what we think about, what should happen is we're moving into the lock zone, where we think there should be less pore fluid pressure. That would be associated with less reflectivity. So maybe this is showing something about this change from a higher reflectivity region where there are elevated pore fluid pressures along the plate interface, which would also be similar to that low velocity zone feature that I just showed. And it transitions as you go up dip into a region of no reflectivity. So again, using different data, but coming back to the same question, what does the transition from locking to stable sliding look like? We see this up-dip disappearance of reflectivity, and it's likely, the simplest explanation, given what we know of the region, is that it's reflecting what we would expect to see associated with that sort of structure into a more sediment and fluid pore plate interface. But you should be questioning this, because if you remembered, when I showed you this plate interface here, that station was here. And that is farther up dip than where I was just telling you the reflectivity is ending in this region. It extends about 35 kilometers farther up dip. So what is going on? Why are we seeing this low velocity zone that seems to indicate the presence of either elevated pore fluid pressures or sheared sediments underneath that station up here, but it's ending much closer to the coastline a little bit further north? And what we did was just a qualitative investigation looking at a couple of other stations along the coastline and a couple of other shot lines. Now, these are no longer 2D shot lines, so we really can't do the 2D investigation of the ray paths. It becomes a much more complicated problem. But we qualitatively looked at the data, and we noticed that there are some of these abrupt variations in amplitude at these different lines, at these different stations. And so what I'm showing you here is just a rough map where the red areas indicate at the plate interface where we think we're observing high amplitude arrivals, and the gray lines indicate at the plate interface where we think those high amplitude arrivals are absent, which again may be a proxy for the high amplitude arrivals would be a proxy for elevated pore fluid pressures or sediments. And what you'll notice is that it seems like in this region, as you move farther north, that there's this, it's not continuing as far up dip. With these long strike lines, there's a pretty abrupt end to this feature in this area, whereas further south, these high amplitude arrivals seem to be extending farther up dip. So this is, again, qualitative. We need to go through this a little bit. This was the last part of my thesis, so it was the very, very last thing I was working on, so this still needs a little bit more work. But maybe there is a decent amount of a long strike heterogeneity in the plate interface structure on the order of tens of kilometers. And maybe that might be related to some sort of variation in slip behavior. We don't have the data right now to know that, but starting to image these structures is going to be one of these first steps to really understanding that. So in conclusion, I'll just summarize all of my results. And so we have new seismic data providing constraints on the Cascadia subduction zone, and we've had kind of a multi-scalar approach, both looking at this broad, entire lithospheric structure of the subduction zone and more detailed imaging of the plate interface. We see that plate cooling models with uniform grain size can't really explain the slow velocities beneath the Juan de Fuca ridge and the fast velocities beneath the center of the plate. See a long strike variation in phase velocities that are related to the volcanic arc and back arc, which are consistent with variations in magmatic productivity. Variations in the Forearc seem to align, the slow velocity seem to align with Bouguer gravity anomalies, and regions of high tremor density are consistently down dip of the slowest Forearc velocities. And we'll still need to do a more careful examination of the effects of the slow accretionary wedge to determine where in depth these velocities are coming from, but it suggests interesting variations along strike. And we see, at least in places, that a low velocity zone seems to be extending into this broadly locked region. However, that it seems like there's heterogeneity along strike, perhaps indicating a more complex plate interface structure. So, thank you.
Questions?
Hi, Helen. So you showed us the profile of the velocity with depth, where you had that plate in.
Yeah.
So what is the thickness of that? Can you say anything about the thickness of that?
So this plate interface low velocity zone in this model is about 1 kilometer thick. Okay. One thing that is a little bit tricky with this particular method, and this is something that on my list of things to make it a more robust result, is that the way the Bayesian inversion works is that it goes through and generates a model and sees how well the model produces synthetic data that fits the observed data and decides to accept or reject it, and then puts all those final models together, and that's how it comes up with this, kind of probabilistic range of models that are accepted. The trick is that a feature like this could be composed of a bunch of models that are all, say about 1 kilometer thick, or it could be composed of something that's a bit thicker, but they're all kind of overlapping on that kilometer region. And so I haven't looked into what the individual output models are in terms of, what the resolution, because it is quite thin and it is a bit surprising that we have the resolution. But, this is also, it's entirely data driven, so it's not going to be there unless the data require it. So, yeah.
And does its velocity place any constraints on, if it's maybe pore fluid, can you place any constraints on the quantity of pore fluid or anything like that?
Yeah, so it's not something that we've looked into yet. I mean, in theory, yes, you could, but yeah, that hasn't been something that I've looked into yet. Really the main thing that we're still working on right now is getting this result for more of the stations so that we can see with the receiver functions, how continuous this feature is, and then, move into thinking about more details about what the pore fluid pressure might actually be to have to cause velocities like that. But yeah, we haven't thought about that yet. Yeah.
So I'm wondering how you interpret the velocity drop around 30 kilometers?
Yeah, so that's an interesting one. Yeah, so we haven't thought that much about interpreting it yet. However, it's interesting because, so Sam Bell's surface wave results for the exact same region, they're almost identical. So it's definitely being driven by the surface waves. And if you notice that it's, the probability of it being an abrupt boundary is much lower than anything up here. So I actually would say that it's probably not being driven by the receiver functions. It seems to be driven by the surface wave result, that it needs to get slower as you go down with depth, which would also then maybe perhaps imply that it's a more gradual boundary than that. But yeah, in terms of what it is, that is still a question. I know that there is a paper that just came out that is looking at LAB structure, and I haven't compared their results to that. I'm pretty sure it's deeper, but you know, the LAB, it's only 10 million year crust, so it shouldn't be that deep in this area. But I think it is still deeper than that. You know, another interesting thing is actually how fast it is here in terms of, you know, these questions of whether or not there is any evidence of serpentinization in the mantle. This is very fast, and this would suggest at least there is no evidence of serpentinization in the mantle right here beneath the subducting Juan de Fuca crust. But yeah, it's mostly, this result so far we focused on the plate interface structure.
If you only use surface wave, does the lower crust, does it still have the high velocity below that, above that drop?
Sorry, which?
Yeah, that area.
Yeah.
If you only use surface
Yeah,
wave,
so actually, I think I actually have. I haven't tried it only with my surface waves, but yeah, so this is, for example, the comparison with the shear wave velocity profile for that grid point from Bell et al., and he just uses surface waves. The difference between in the upper 15 kilometers is the upper 15 kilometers is completely fixed a priori because they don't have sensitivity. But yeah, if you'll see here where their sensitivity does pick up, it agrees pretty well. So that's why I say it seems to be driven by the surface waves.
I have a related question on this. Isn't that the 30 to 50 kilometers where most of the tremor activity was observed? So if you plot the BPBS ratio from other people's data, how does that align?
So this is all still up dip of where tremor is.
Okay.
Yeah, so this is going down from a region offshore, and this is within the subducting Juan de Fuca mantle. It's not where the tremor is occurring. Yeah.
Related question. So in the first part, you mentioned you compare with the tremor depth and then with your 40-second surface wave. I just wonder what is the depth range for the 40-second.
Yeah. So.
And then how robust is that?
Yeah. So again, one of the things that I said is that the exact depths are a little bit shaky in the Forearc because of the slow velocities. Let me see if I have. Oh yeah, so this is outdated. I updated these models, but this. Okay. So these are sensitivity kernels, and this is just using a predicted velocity model for oceanic accretionary wedge continental. So not an inversion, just based on what we already think we know about the area. And this is what I was saying with how you get for 10, 15, and 20 seconds, your sensitivity gets way shifted up relative to oceanic and continental. It's problematic. But so if you go to 40, by then, it should be roughly sensitive around 50-ish, 60-ish kilometers, although it does, potentially still have these weird, peaky things going on in the shallow part. So it's a little bit tricky. So yeah, that's why I hesitate a little bit in terms of interpreting it too much specifically what this structure might be, because there's still, even at those periods, maybe a little bit of a shallower shift. Yeah. Does that?
You showed us there's a high velocity anomaly in the center of your plate. And has anyone done volumetric? If so, does the same anomaly appear in those maps as well?
Sorry?
So you showed us in your phase velocity maps that you had a high velocity anomaly in the center of your plate. But I'm curious if the same anomaly appears in volumetrography.
Yeah, it does. Yeah. So Burns et al. Had a recent body wave paper that sees the same sort of anomaly and also an anomalous gradient where it seems to be rapidly cooling relative to the ridge. Sam Bell's surface wave result sees the same thing. Zach Alon's attenuation sees particularly high attenuation beneath the ridge that gets rapidly lessens in the center of the plate. So it seems to be something that is being seen, from various areas of seismic imaging. One of the weird things, however, though, is that if you look at the bathymetry, it doesn't look all that anomalous, right? Because the bathymetry you would expect also has a characteristic plate cooling signature to it. And you could imagine if you had some sort of downwelling, that should be evident in the bathymetry, and it, at least to first order, doesn't seem obvious. So I think that's where we're having a little bit of hesitation still figuring out exactly what's going on there. But definitely the fast center of the plate is something that seems to be popping up robustly in various seismic studies.
I have a question related to this slide. So how, I guess in my office we talked about how assumptions about shallow structure can substantially influence inferences about deeper structure. And I'm curious how sensitive these differences are. We're talking about differences that are on the order of about 100 meters a second. How much can they change based on what you assume about shallow structure?
So we did some tests. So the place where we expect the biggest issues with shallow structure would be as we get closer to the deformation front, which is where we get the thicker sediments. And we're using a global sediment model, Divins 2003, which has its problems. And definitely compared to the higher resolution active source studies in that area, they are seeing thicker sediments. And we did tests particularly associated with these slow areas to see if we raise it. These are about at like 2 kilometers, and we raised it up to 4 kilometers, which is about the maximum that this active source sees outboard of the deformation front. And while it helps, it doesn't entirely get rid of those signatures. I mean, of course, there could still be issues in terms of uncertainties in the velocities of how we're, specifying those for sediment, and things like that. But at least, doing the best we can right now with what we know about the uncertainty in the sediments in that region, it seems like they're not going away.
What do you assume for the crust in these, when you make a prediction for thermal plate cooling?
Yeah, so for the crust, we're just using, what's it called? I'm blanking on it, Garrity and Dunn Atlantic model. And we haven't tested variations, how much of a variation in the crust would affect, but I think it would be that significant, but it'd be something to think about. And I mean, I guess, another thing too is that, right, I mean, for example, there's the active source is seeing bending in the plate, fault related, and that does have some sort of an effect on seismic velocity, and there's no way we're accounting for that, in these parameterizations that we're using. So, that could be something, but it doesn't seem like these exactly coincide with where plate bending begins either. It seems like they are elsewhere. So, yeah, I mean, I completely agree with you, but in terms of at least doing our best to try the reasonable scenarios that we have of prior information without, going into the step of really doing a more thorough full velocity inversion. I think this is where we're at right now. Yeah.
Can I ask another question? So if you go back one slide, or forward one slide, I think it's the same slide.
That one?
Yeah.
Yeah.
Okay, so here you show us ambient noise phase velocity maps, and then you show us some teleseismic maps. And What I'm curious about is, I know, there's limited frequencies at which these two will overlap, but presumably at 20 and maybe 40 seconds, you could compare them. How do they look like?
So you can read this in the paper when it comes out. But we compare it at 20. 20 is the only one we can compare it at. The problem with the ambient noise is, so actually, the ambient noise, we have to pretty much exclude almost all of the shelf stations from the ambient noise because it overlaps with infragravity waves are affecting the noise in that period. And by the time you get to 40, you're getting much deeper stations being affected by infragravity waves. So we can't go up to 40 with the OBS data.
But on the on-land, onshore part, you could.
Yeah, we could. We just, yeah, I guess, we could do that. But I guess, well, an issue with that, though, is we'd have to kind of deal with an entirely separate inversion because we'd have to worry about the bad data from the OBSs influencing things.
I didn't mean to distract you. What does it look like at 20, I guess?
I'm trying to see. Actually, I will show you in the interest of being completely honest with you.
No, I'm just curious.
Yeah, no. Okay, so I'll show you two things. That and that. Okay, so this is the difference at 20.
Okay.
And okay, so shoot. Blue is ambient noise is slower. And what you'll notice is most of this is okay, except really right along the coastline. It's pretty atrociously different. And this area in the southern, southeastern corner is also not that great.
So this is a 20-second map, difference in velocity between two ways of constructing it.
Exactly,
Okay.
yes.
For the geochemistry.
Yeah. And yeah. And also remember 20 seconds, the range of velocities that we're seeing for those maps is on the order of 1 kilometer per second. So when it's, and the average difference is actually about 0.1. So 0.1 relative to 1 kilometer a second is not that bad. But when you get up to here where it's 0.4, that's pretty bad. The issue that I think happens is if you look, this is just looking at the standard deviation at different periods, average standard deviation for offshore and onshore grid points. And you'll notice, 20 for the ambient noise really rockets up. Even 20, we're pushing what we can do with it. And teleseismic, 20 is comparable, but it's still higher than the subsequent periods around it. And so, unfortunately, I think it's just that 20 seconds for both of these data sets is relatively uncertain compared to its adjacent periods. I don't really know why 20 seconds at ambient noise is so rough, but maybe it just does have to do with the fact that at that point you are starting to run into these ocean noise problems. And also, it's just the way the rate geometry is. But I think, it'd be great if we had more agreement, but that's what we chalk it up to, is that it really is our most uncertain measurement. And the other thing is this area right here. There is a slight difference in the station geometry that we're using for ambient noise and teleseismic. And this area just for the ambient noise isn't as well resolved because we don't have a full grid of stations here. We just have kind of one station in the corner. So that's what that's coming from.